All right, so good afternoon, everyone, and welcome to the next installment of the Princeton Wireless Distinguished Seminar Series. Today, we're super excited to have Harish Viswanathan here with us. He's the head of Radio Systems Research Group at Nokia Bell Labs. And Harish joined Bell Labs in '97, and he works extensively there on wireless research, ranging from physical layer to network architecture protocols, as we're going to see in this presentation, including multi-hop and cellular relay. He's published extensively, over 100 publications, and he's in the corporation CTO organization at Nokia Bell Labs. He's a CTO partner, and he advises the corporate CTO on technology strategy through in-depth analysis of technology and market needs. And so with that, I'll hand it over to Harish. Welcome, and welcome.
Yeah, thanks, Kyle, and thanks for inviting me to this seminar series. As you all may know, that cellular industry introduces a new generation every 10 years or so. And we expect 6G in the time frame of, say, 2028 to 2030. But the research for that starts already 10 years in advance in the industry research labs. So that's why I'm here to talk to you about 6G while we are still in the midst of 5G deployments. So I want to share with you today the 6G vision and some of the technologies that we are working on, how we think 6G may change the world. That is the focus of my talk. As I said before, please feel free to stop me and ask me any questions or make any comments. Okay, so let's start with the historical perspective where we have come from. So here you can see since the 1990s, almost every 10 years, like I said, we've had a new generation. And in 2G, it was all about voice, so making voice mobile. And then SMS was another application that wasn't really used at that time all that much. And then in 3G, voice became a sort of a mainstream application, and the focus in 3G was about optimizing the voice for capacity, reducing the cost of voice. And then we introduced broadband data as the new application. And towards the end of 3G, smartphones started becoming popular and pushed the limits on broadband data. So then if you look at 4G, what happened during 4G, voice essentially became zero marginal cost. So you had unlimited voice with the basic data plan. And then we were really focused in 4G about optimizing data. So the use case of 3G is now being optimized in 4G. And the use case of 2G essentially becomes unlimited in 4G. And then we introduced video streaming and machine-type communications or IoT communications as the main new application in 4G. And today in 5G, we are starting to see unlimited data. I'm sure many of you already probably have unlimited data plans with 5G. This is, I think, following the same trend from the previous generations. So we are optimized data to the extent that it can essentially become unlimited for, of course, some access price. At the same time, we're optimizing IoT still, making it more energy efficient, and then optimizing the video streaming. And in terms of new applications, what we think 5G will introduce is mainly this industrial IoT, so extending the use of cellular into the factories for automation, into the harbors, mines, and places like that. And for the consumer, it's going to be more interactive video, augmented reality, sorts of applications, eventually when 5G is deployed in a widespread fashion. So the lesson we learned from this is every generation is about optimizing the use cases of the previous generation, and at the same time introducing new use cases. So if I think about 6G, then it's really going to be about optimizing this industrial IoT. I think industrial IoT will really take off in 6G. We will do a lot of experimentation in 5G, especially around this low latency and high reliability, and they become more optimized in 6G. Likewise, the interactive video will become mainstream, perhaps in the 6G timeframe. But then we will introduce again new use cases, and we predict that it's going to be two things which are really related to each other. One is what I've called dynamic digital worlds, which I'll talk about next. And of course, the massive scale artificial intelligence is going to become prevalent in the world, and 6G connectivity needs to support that. Going further, then what is this dynamic digital worlds that I'm going to talk about? So it's really what is going to unleash human potential. So it can be thought of in 3 different categories. The first one I would say is about enriching human experience. So what it is going from the XR and AR of 5G to true digital representation of the physical world at every time, instant, and spatial location through the use cases like high resolution mapping, which will then enable many other use cases. So we say multimodal telepresence. So it's not just audio and video and sharing, but maybe many other forms of sharing, maybe your emotional state, maybe in more rich representations along with the environment that you're in, making you feel like you're actually there. That's what we expect in the time frame of 6G. And then if you think about the industrial collaboration, you can think of doing some sort of prototype designs between collaborators across different factories using both a combination of physical and virtual objects. So the entire workbench is digitized with high resolution and be able to transport that to another location. Of course, this calls for new devices like the glasses or other wearables that the industry is working on. But I think this is where we are headed, and this will certainly enrich human experience. Bring things to you, like we brought voice to you, then we brought data to you, and now it's bringing the whole world to you through digital worlds. Then it's about augmenting our intelligence. We are going to rely more and more on machines for helping us make decisions, process data and information, and that trend is going to continue. And the role of the networks would be to support such use cases, gathering and processing data. And so it could be in the form of more enhanced digital assistants, early versions of which we are seeing today. And in training them, right? The role of the network would be also not just as a service, but also in creating those services. And it all needs to be done with security and privacy. And that itself is about gathering data and communicating the data so that it can be processed and monitored. And then on the human front, we can learn a lot more about ourselves with more sensors. So this is something we see as augmenting our intelligence in the future, again, helped by technology as well as connectivity. And then the last one is about enhancing human productivity. And this relates to, again, these digital worlds applied in the context of industry. More robots in place of cooperative communications between robots in factories, or maybe even robots at home. And then things like remote driving, maybe not self-driving, but remote driving could become a possibility. And that would require a very rich representation of what the vehicle is actually seeing in its environment. Just like we are able to do remote control of drones, we should be able to do that for terrestrial objects. I mean, it's starting to happen, but they become more and more common in the 6G timeframe. And then finally, drones and robot swarms and things like that, facilitating that. So if you think about what I just talked about, you can think of it as this unification of this physical world, the digital world, and the human world. And this is our main sort of vision for 6G. So the digital world in real time captures both the physical and the human world, so to speak, in a way that it can be communicated and experienced anywhere at any time. So to be a bit more concrete, people always ask, okay, all that is fine. What does it really mean? And what does it mean for technology? And why do we need new technology to do all that? And so I have this view of what is happening in 5G on the left and how it's going to change in the 6G timeframe. So on the 5G, you can see that we can do augmented reality games as one example of what 5G is going to enable. And with even more capacity and data rates, and especially uplink capacity, we get to this what I just described to you, the dynamic digital worlds. And then the technologies that will be needed to achieve that which achieve the higher capacity and the data rates would be basically more spectrum and more extreme massive MIMO, because that's the way we are now delivering the higher capacities. And of course, machine learning will be needed for actually creating the experience, processing all the data, etc. And then the next one on the left is today 5G can have latencies that are fairly low, that enables remote monitoring, remote guidance of various machines, and we want to go to real-time remote control. And main task is to increase the reliability in a wide area context with wider bandwidths, etc. Coverage is still restricted in the sense that there are a lot of places that are not covered in the world, like for ships or even in rural areas, the coverage is a bit non-uniform, and the integration of non-terrestrial networks, which we think will start to happen in the 5G timeframe, but fully established by 6G, would give potentially global coverage. And then the technologies we need are spectrum and RAN sharing to enable that. In terms of the deployment and operation of the network, we've talked about self-optimizing networks, and we are trying to push that to what I would call zero-touch automation with the energy efficiency. And a lot of this will, again, rely on machine learning techniques for the optimization involved. The 5G architecture is starting to become more cloud-friendly, deployed in the cloud as cloud-native functions, microservices. And we have to take this to the next level. So instead of specialized operator clouds, it's going to become more heterogeneous in terms of the kind of cloud environments where the network can be deployed, private, public, etc. And in order to facilitate that, we are, of course, starting the network disaggregation. That's going to continue further. And we need to also simplify the architecture. There's opportunity to make the functions more modular and simpler and involve more open interfaces. So I think these are the things that we expect in the 6G timeframe on architecture. And then the last one was very important. We already have very secure networks in 5G, but we need to take it to the next level where the networks are more trustworthy, in the sense that you can have multi-vendor networks, and we are able to verify software. Today, there's a lot of geopolitical tension associated with this trust, and we want to maybe address that and build resilient systems for whatever reason. If the systems are non-functional, then other systems take over, etc. So these are some of the big changes I think we are going to expect going from 5G to 6G. And then in the context of a campus or a industry, we have the low latency and high reliability starting to happen in 5G, and we really need to optimize that. And then 5G also has this thing called reduced capacity, or expanding the use cases of IoT, like video cameras that are now everywhere in our homes, but maybe will be in use in a wider sense. These applications are being considered for 5G with different capabilities. And we will expand the range of use cases under IoT by going after even the zero energy devices like RFID tags. So can we enable that in a wide area context? And then localization is critical for many industry applications, and we can expand that with increased precision, as well as the network providing more information by being a sensor as a whole. So to summarize then, we see the role of 6G technology in this sort of 6 domains. And the rest of my talk is going to be about the research that we are doing in each of these domains. So the one that's called new spectrum technologies, this refers to what new spectrum we could expect and what new technologies we need to make use of that spectrum. Then we pay special attention to the use of AI and machine learning down to the air interface, the radio transmission and reception. We see a lot of potential there, not necessarily in terms of performance, but in terms of being able to reduce the cost and make it more energy efficient. And so we are exploring a lot of things in that space that I'll talk about. then yes, this whole idea of how we can make a network as a sensor, why we think now is the right time, and what are the potential use cases specifically, and the challenges that are associated with making that happen. Extreme connectivity is, I probably won't say much about that, but this is the next generation version of what is called URLLC, or this ultra reliable low latency in 5G. Then a little bit on the architecture innovations that we can expect in the 6G timeframe, and finally on security and trust. What are the new challenges? I see a raised hand there. So
yeah, that's me. I'll take you up on the questions, inline questions in the talk. I was actually going to ask you before you mentioned high connectivity, about high connectivity scenarios, and do you have any thoughts about how this changes the architecture of the network when you have so many low data rate devices that you want to remain connected to? Even a massive MIMO, base station RAN scenario, you'll have many, many more devices than antennas. And so, do you have any thoughts there about what that implies?
Right. Actually, the first step in accommodating that was the separation of the user plane and the control plane, which has already happened. If you think about this narrowband IoT or even LTE, we've done that. And the main reason we did that was it allows the control plane to scale separately, right? So when there's very little traffic, you still have a lot of control plane messages. So that's one aspect of it. I think another advance that we can expect, and we sort of pushed for it in 5G, but it did not, is the connectionless transmission. So in other words, devices that are able to just wake up and send a packet and just go back to sleep. You don't have to have a lot of messages going back and forth to establish state for the device in the network. I think this is an interesting architectural change to scale IoT.
And this is, this is distinct from cell-free MIMO, correct?
Yeah, it's different from cell-free MIMO. That's right. Yeah, I'll talk about MIMO under this new spectrum technologies umbrella. That's where we think about it, because we want to apply that to different bands. So I hope I answered your question.
Thank you. Yeah.
Okay, so yeah, I don't have obviously time to go through all of this in great detail. So I took the approach of giving you an overview of these and the challenges in these different areas. Okay, so let's start with the AI as the first topic. So obviously, this is a new tool that's available to us, really, and we are interested, like many others, to understand what this tool can do for us. So the picture you see here on the left, in the top, is how we think of our physical layer implementation, the transmitter and the receiver with the various functional blocks on the transmit and receive. And already in 5G, we are exploring whether we can replace some of these individual blocks with deep learning or other types of learning versions, mainly in the 5G case, to see if they would be less complex for the same performance. But the real disruption, if it happens, and again, there's a lot of research to be done still, is when we can combine multiple such blocks into a single big neural network. So all of the processing that was highly different for these different functions in the receiver all look essentially the same and are all combined into one. And even more interesting in the 6G context would be what are the changes we can introduce on the transmit side by also learning, for example, the waveforms or the constellations and things like that, right? New modulations. Not necessarily always for better performance. It's more for more robustness, as well as ease of implementation and lower cost. Because by making these neural network versions of the traditional functional blocks, we believe that it can be implemented more efficiently on, say, one type of acceleration for this neural network. Could even be analog computing in memory, and that can make the system a lot more efficient from an implementation point of And the other reason is for our own sake, the way we do research way we do development, product development, can be highly simpler if we are able to do this sort of an implementation. So those are the reasons why we are doing that. And there are a lot of challenges associated with that. Yeah, I mean, investigating how far we can actually push this. Can we really achieve our goals with this sort of an approach? So it's all work in progress, and I want to give you a few examples. So if you look at what I call the deep RX, this is taking the conventional receiver architecture here with these different functional blocks and trying to replace some of them. And this is for MIMO systems with a single deep learning block. So you can see mainly the channel estimation and the detection. What is called as the equalization demapper is really the MIMO detection. So these are combined into a single functional block. And this is sort of the first step towards our vision that I just talked about. And it turns out that this actually is pretty good and is able to do things up to at least 4 layers. Layers here basically represent the number of individual data streams that we are trying to detect. So it's not really like very large number of simultaneous data streams, but at least we have it working in the simulation experiments for up to 4 layers. And the interesting observation is it helps us push the speeds to which it can work. So on the left, you can see the Doppler shift for the devices, and the blue lines are the deep RX versions, which have pretty good performance independent of the Doppler shift, whereas the traditional ones, they tend to become worse as the Doppler increases. And of course, the performance depends on how many pilots we introduce. And this is actually one of the things that we're observing again and again in our deep sort of physical layer work, that it's pushing the envelope on the scenarios that we can do well at, right? So today, massive MIMO works mostly for low speed. It doesn't work for higher speeds. For these reasons, you know, the number of channels you have to estimate and the process makes it really difficult to make it work. But then maybe these versions tend to work better for higher speeds. So that could be one advantage. And again, this shows the performance with the coded block array, a substantial improvement of about 2.5 dB on the link performance. So it's sort of promising. And then another area, especially thinking about what new we can do in 3GPP standards for 6G, is to introduce this in the transmitter side as well. And now you're talking about end-to-end learning. And you can have nonlinear power amplifiers in there. So far, our whole system design concept assumed that the radio is highly linear. And we then designed our modulation and coding schemes for that linear system. But now we have the opportunity to consider maybe designs that can work for pushing the PAs into the more nonlinear regimes, right? And we of course have to still meet the constraints on, say, the adjacent channel leakage. And these plots here show that when you do end-to-end learning, you're actually learning constellations that are not that similar to what humans would do, or like we don't use the 16-QAM or 64-QAM like constellations, but rather more asymmetric constellations. And this actually is allowing us to do pilotless, so to speak, in the sense that what we did was to not consider specially pilots and use the pilots on the receive side, but just give this the learning problem from end to end and see if it can sort of create its own pilots, etc. But what the system ended up being is this sort of asymmetric constellation, which turns out to be enough to detect the received signals. Because if the constellation is asymmetric, you can learn what the channel did to that when you observe a number of symbols. So this is another very interesting approach, which changes the paradigm of how we design our communication systems. Okay, so then let me move on to the spectrum. So what you see on the
Harish, can I just ask you a couple of questions here? So this is very interesting. Could you comment on the learning process here? Maybe that's one. And number two is, we also talk about reliability, right? So could you also comment that in these approaches where we are depending on end-to-end learning, is there a chance that the reliability might suffer as a result of uncertain situations which may not have been, statistically present during the training data?
I think, yeah, so maybe the second question first. Yes, that's definitely possible. So I think this is why we need a lot of experience with these schemes before we can really deploy them. So, we are building, actually in 5G, almost a separate, I would say, product that's based on these approaches just for testing and trials. Yes, I mean, we try to train them on a wide variety of channels, both simulated, emulated, as well as measured channels. But it's always possible that there are these unique channels that for which it doesn't work. That is a concern, and I think the only way to address that is really to experiment more and more and see if it actually works. I mean, synthetic data is a good way. I think because we can generate a lot of data and create all kinds of crazy scenarios for the system. So that's how we think we can address that. And then on the first question, how we train them, yeah, it's end-to-end training. So there's a loss function that basically measures the error between the input bits and the output bits, and the whole chain here is sort of differentiable, and so we can do the standard gradient descent, taking the channels in the middle also into account because they are linear transformations. So the whole thing is treated as one giant network, and we basically train both the hyperparameters of both the deep RX as well as the deep TX at the same time.
Thanks.
Okay. All right.
Sorry, if I can, could I jump in with a related question? I know that there is an advantage of in coding, in integrating coding, error control coding with modulation when you start to go to non-rectangular constellations, like what you have on the picture. Mm-hmm. And so, have you kind of compared your approach with deep learning with these prior approaches in air control coding that look at nonlinear constellations, non-rectangular?
Right. So we haven't combined the coding and the modulation into one deep learned block yet. I think the training for that is quite challenging, is our observation. If you want to do end-to-end learning with the coding and the modulation and MIMO, I think it's extremely difficult to do still. So that's why we haven't done that. So I mean, so our coding is the standard LDPC coding, but then we only changed the remaining blocks so far. So yeah, so in that sense, we haven't compared against the versions of the what you're proposing so far.
Thank you.
But yeah, I mean, I'm sure there's potential improvements possible when we take coding into the picture here.
Thank you.
Okay, so spectrum-wise, I think I want to say that the current focus of the industry is in really these two bands for 6G. So the rest of the pictures you see here is already the 5G bands, all the sub 3.5 gigahertz, sub 6 gigahertz. But for 6G, we would really like the various FCCs and their equivalents in different countries to allocate more spectrum for cellular in the 7 to 15 gigahertz. Of course, there's a lot of talk about the sub-terahertz, but considering how millimeter wave has been used, I think the sub-terahertz would be mostly for in-band backhaul-like applications, potentially, I mean, in-system backhaul applications. Maybe some restricted access applications indoors, or some very short range outdoor applications, hotspots, etc. But every new generation needs some real new spectrum for it to make a difference. I mean, because the amount of spectral efficiency gains we get pales in comparison with the scale we can get by adding more spectrum, right? I mean, it's very difficult to double the spectral efficiency or triple the spectral efficiency, although massive MIMO has done that. So beyond that, we also want to do it with more spectrum. So we've been pushing the FCC, for example, or having discussions with them to introduce additional spectrum. Of course, it's getting harder and harder, but we hope that we get this prime spectrum of 7 to 12 to 15 gigahertz as the new spectrum for 6G. And if we do have that, okay, and then there could be some spectrum in the really low bands for new IoT applications. So what can we do with this new spectrum, right? The reason why this is very attractive is basically we can pack many more antennas and still do things that are similar to what we're doing now. So this picture here on the left shows roughly what we do today at 3.5 gigahertz. So a 256 element array, 128 cross-pole elements basically, and the bandwidth is of the order of 100 megahertz for most deployments. And in this we have 64 transmit-receive chains. So essentially it's hybrid, but then the digital analog part of that is really fixed vertical beams. So that's what we have now. But now if we scale up the bandwidth even by a factor of 2, we're able to scale the number of elements by a factor of 4 on the 2 horizontal and vertical dimensions, keep the array size the same. Now the question is, how well can we exploit this? And will this really give us another factor of 2 or more in increase in spectral efficiency? How do we achieve that? So it turns out that our early studies basically show that this is a good approach for us. I mean, considering that massive MIMO is sort of the bread and butter of 5G, the main macro solution, we can extend that to these bands, make them more powerful. 4 times, and coupled with 4 times the bandwidth, we can almost get 20 times the capacity if you do achieve the 5x spectral efficiency. And it turns out that to achieve the 5x, we also need to scale the number of antennas on the device, which again will be possible because you're going to higher bands. So that's what our attraction is. And then we have to be able to come up with flexible designs that work for different bandwidths. Because if you look at the spectrum landscape, it's very difficult to get contiguous bandwidth that's substantial, 400 megahertz, and the same in every country. It's never going to happen. So we need highly flexible radios. That's another big challenge. We don't want to build radios that are sort of narrow band, and then you have to build separate radios for different bands or different bandwidths. So that's an interesting transceiver technology challenge. But with all that, if it happens, then we can actually boost capacity another factor of 20 and support all these grand applications that I talked about in the beginning. Now, there are some challenges, and I want to highlight 2 things here. So if you rely on analog beamforming, then there are some implications. And we would have to rely on this, for example, when you don't know the channel. For example, for initial transmission, before the device is in connected mode, you don't know where the device is, what the channel is, then you have to rely on something like this. And what we have observed in our measurements is, yes, you can increase the array size, but it doesn't mean that your beamforming gain is going to increase as well. So the plot you see here is the effective beamforming gain for different array sizes and the beam widths, the half power beam widths. And in theory, the beam gain should scale according to this black line here. But in practice, because of scattering, so because of the angle spread, the gain will saturate, right? Of course, this is for an outdoor macro-like environment, or I guess, rooftop type macro. And so we have to be cognizant of this. So then this poses a challenge for coverage, and that's an important challenge to address. How do we solve the coverage problem? Because as you go higher in frequency, we know that the propagation is becoming more difficult. And so if you keep the array's aperture the same, you can go as far in distance as you can with the lower frequencies. So compensating for that with beam gain will start to be a problem if you really believe this, which is what our measurements show. So then we need to come up with ways of learning the channel and doing a digital beamforming. If you're matching the beamforming to the channel, then of course you're not limited by this sort of limit on the gain, because now you can form your beams wherever you get a good signal strength, right, in whichever directions the signal is coming from. So this is why it's going to be critical to do digital beamforming, but then digital beamforming is expensive in terms of size, power, and cost and weight. And so somehow we have to innovate and be able to do low-cost versions of that, or do analog beamforming with some kind of channel knowledge and steering and things like that. So that would be the challenge for really exploiting this new spectrum. So then a lot of talk about IRS or RIS, the intelligent reflective surfaces, etc. So the vision that I've seen in a lot of academic literature and also from other players is to say that we can have sort of on the walls of big buildings some kind of a smart reflective surface, and then the access point can sort of reflect. You can control the direction of the reflection, etc. And we did some work based on our own measurements of the signal propagation in New York, for example, around the corner. So this is what we would call around the corner. So this is one street. I hope you can see my mouse here. And then this is the cross street, and you're doing propagation around the corner. And so the question is, does it really improve coverage in this in these places, right? And it turns out that a 1 square foot RIS is only a little bit better than native scattering. So remember that there's going to be a lot of clutter, street clutter, like poles, buildings, which are also going to scatter the signal. And so the black line here is actually the measurement that was made around the corner in New York City with our measurement equipment at 28 gigahertz. And so if you compare the signal strength that we measured against what an RIS could do at the corner, it's not that great. So my main point is that we need larger RIS to see the benefits. I mean, yeah. So the question then becomes, okay, is it possible to build a large RIS in a cost-effective way? So that would be an interesting question. And then how do we control these things? If they get larger and larger, the control problem gets harder as well. So those are some of the challenges to be addressed in using this.
So Harish, maybe another quick follow-up question. This is very interesting. Thanks for sharing. I guess this also tells you that you may need some gain on the RIS, right?
That's another way to go. Yes, that's certainly valid, right? If we don't rely on just passive, then maybe you can live with a smaller RIS and with the gain on that. Yes, that's certainly a possibility. Yeah, that's a good point. Okay, so then moving on to the next topic, the network as a sensor. So over here, we observe that as we go to 6G, we will have to densify somewhat. There is no option but to do that, because as I said, as you go to the 7 to 20 gigahertz, getting the same coverage is going to be hard, even with the beamforming. So chances are that eventually we will densify, and densifying means that we are closer to the objects that we want to sense. So that's going to help us. We are also going to wider bandwidths. So we are shooting for 400 megahertz instead of the 5G 100 megahertz. And natively, we're going to have a lot of AI and other signal processing built into the system. And finally, all systems are going to be based on MIMO and beamforming. And so with all this, they're all not helping just the communication, and they can be put to good use for doing sensing. And you can think of a wide variety of applications that we can support with that, right? So it could be localization as one example, outdoor localization, which we are already doing in 5G, but we can add more to that in terms of precision or other information like imaging. And of course, if you really have terahertz, then of course you can do a lot more. So that is the attraction. I mean, at some level, if we are really successful with this, we're going to make sensing as ubiquitous as voice and data. Today with your smartphones, wherever you are able to talk, browse the web or whatever. And imagine if we can create something like that with sensing, have all kinds of sensor data available everywhere. And now, since all these cells will be, deployed everywhere, that's a place from which to do the sensing. But there are a lot of challenges. So, how do we combine communications and sensing? Do we do new waveforms? Will they work better, or can it just be OFDM-based radar? Because traditionally, radar has been based on other types of waveforms. So then the question arises, do we need to multiplex different things, or can we manage with just OFDM again? From a design and standardization point of view, we need to take channel modeling to the next level for sensing. You need to be spatially accurate, capture all the scattering properties better, because if you're trying to do object identification, then you need to know exactly what the object does to the signals. So then the channel modeling gets harder. Then, of course, from a design point of view, we have the beam sweeping and resource allocation sort of procedures today for communications, and we need to extend those to sensing. And then using multiple bands is another interesting idea. So that helps with more accurate characterization of the object. And then localization algorithms. Today, our solutions are good for localization, but we find that we need many, many access points, right? It's not enough to have just 3, because if we have just 3, the accuracy is not that good. So you need to have links to maybe 6, and having line of sight links to 6 is very hard, even indoors, because then you have to increase the density of deployment. So then we need to work on new ways of doing localization with fewer access points being able to pick up the object. So those are some of the, I think, very new challenges that come up in the context of sensing. And the last one is what I'm going to talk about a little bit, the object identification, because we did some interesting research here. So the point is, how do you train these sorts of delayed Doppler images, right, to do object identification? So what the cellular system is going to see is something like this, right? It's a typical radar plot. And what a camera sees is this. So the question is, how do we do object identification with this? Obviously, we don't want to deploy cameras everywhere, and that's the reason we are going with this radar-like approach. But at the same time, we want to be able to tell a little bit about the objects in the vicinity of the cell site. And it's a very difficult training problem because of data. Data labeling is expensive. So nobody is going to sit and label all the data, for especially for these radar images. On the other hand, we have a rich data sets for image, and we have very good image recognition systems, which already label data for us for images. And so we are working on this sort of contrastive learning approaches, where we have data that's both radar and camera from the same location, from the same viewpoint. And then we train networks for learning whether the image and the radar plot are from the same view or different view. So that is the error function here, which says whether there's the image and the radar is the same or they're not the same. And then the image size of the neural network is fixed and doesn't have to be trained. And the learning is basically to train the radar processing, essentially. So by doing this, we can prep the radar plots or the radar input for downstream tasks, right? There's no downstream task here other than to say, is my photo and my radar image the same? But then once you train this basic neural network that takes radar as input and produces this sort of answers this question of the sameness or not, it turns out that then the input from this can be used with another network downstream for a specific downstream task. So here's an example. So we used a publicly available data set from car radars, right? So there are data sets that give you exactly what we need, which is from the same location, they have radar images. These are, I think, 77 gigahertz radar images taken from the vehicle, as well as photos at the same time, and they're both recorded. They're made available. And so we can do exactly what I just talked about before, and match the radar images to these objects. And so we said, okay, can we identify pedestrians, cyclists, and cars from these sets of radar images? And this would be the downstream task now. Just from the radar images, look for pedestrians, etc. And it turns out that with less training, we can get fairly good accurate results. So with 95% accuracy, you can actually classify the radar image to be one of these categories. And the potential for this sort of semi-supervised or self-supervised training has been proven to be much more in the natural language processing literature. Like, for example, Google has published results that show that the sort of contrastive learning on natural languages is working really well. And so we're trying to apply that to our object identification problem. But my main point here is something like this is critical to make this network as a sensor really useful, right? Just having radar plots is no use for anyone. And so unless we are able to do this downstream processing, it's not going to be particularly useful for anyone. So this is an important area of research as well. Okay, now on to the architecture work. So there's a lot to talk about architecture. I could, give a whole presentation about this. So here I said, okay, let's focus on a few themes and explain that how we see 6G evolving from the 5G architecture. So on the top left, you have this, what I call the head cloud. I hinted on this before. The microservices-based implementation is going to become much more heterogeneous, meaning it runs on a private cloud without any hardware acceleration, or it runs on an operator cloud with a RAN NIC, NIC being the network interface card. And now a lot of companies like Marvell and Qualcomm are working on specialized hardware to run RAN processing in the cloud, right? So you do need some special acceleration. The CPU from Intel isn't enough. So it could be deployed on a cloud like that, with or without the acceleration. It could be deployed on a web scale cloud, like a Google cloud or an Amazon cloud, or a combination of these. And we want the network to work no matter what the underlying cloud platform is where we deploy the network. So that's what we mean by heterogeneous cloud. And making this automated requires exposing the capability of the cloud at a level where it's not there today, which is what kind of latencies you may get for running certain types of processing, because to run a network process on the cloud means that we have to meet all the timing constraints involved. Then I talk about RAN core unification. So this has to do with the fact that the RAN is being deployed more and more in the edge cloud, while the core is moving from the regional or a central cloud closer to the edge because of scale. You want to fan out the traffic closer to the access networks. So with the RAN and the core approaching each other from the two different directions, and here I'm mostly referring to the higher layer of the RAN, the layer 3 aspects, not the very fast real-time layer 2 or layer 1, but anything about that. So mobility management and encryption, decryption, things like that happen in the base station are moving closer to the edge cloud. So then the question is, do we really need to separate that from functions in the core network, like the access management function and the session management function? Do we really need a separate UPF, the user plane function on the user plane, and then a CUUP, which is the RAN user plane function, right? We now have two types of user plane functions, one in the RAN and one in the core. We have two types of control plane, one in the RAN and one in the core. It was designed like this because the whole RAN was sitting at the cell site as a base station, but things are changing. And so we have opportunity to unify all the interfaces and merge functional blocks, have overall fewer functional blocks between RAN and core. Obviously, AI/ML is going to play a critical role in the automation and orchestration of the network. So there needs to be data and information architecture to gather all the data, process them, and push back, say, new models. So the whole machine learning operations aspects have to be done. And a lot of us in research mostly work on the algorithms and the model architectures, but there's a lot of work to be done on how you execute all this in a real system. The nuts and bolts of operations, gathering data, processing that, and we have to solve things like, okay, we deploy a model in the customer network. Do we still have access to that? How do we update the model there? Do we capture data from the customer? Customer, I mean like a Verizon or a T-Mobile, not the end user. So will they share data with us? And do we run the model updates in our computing, or should they run in the operator compute? And what is our role in that? A lot of questions have to be answered when it comes to that. And so we need to build it into the architecture, the whole data and information architecture, to support all the cognitive networking use cases that we want to do. Then talking about deep slicing. So this is what I would call the extension of slicing, and sorry, nothing to do with deep networks here, but deep here is referring to actually taking slicing beyond resource reservation to actually software that's separate for each slice. If you believe that the network functions are all going to be done as microservices in the cloud, there's no reason why we can't have a different instance of the function in a different slice, because the slice resources are separated. The computing for one slice is happening on a different core or different part of the core than for another slice. And so you could, in principle, have separate software streams. And the reason is to optimize the slice even more. Today, we are optimizing it for, say, quality of service by doing resource reservation. So you have a low latency slice for some very important use cases, and you have a best effort slice. And it's really managed just with resource reservation. But in principle, you could have, in the next generation, software that's different. So one is optimizing the scheduler, for example, for that slice, has a separate scheduler, or it has a separate optimization engine, say, for video flows, things like that. So that's what we mean by deep slicing, taking slicing to the next level. And then the 6G sub networks is all the short range networks that we expect have to be interconnected in the future. So today we have isolated, say, Bluetooth networks, but it would be really good to have interconnection among these, maybe move between these short range networks. And we believe that the wide area network has a role to play in that, being able to move as a whole or move devices from one short range network to another short range network. All of this could potentially be enabled and could potentially have a lot of value for end users. And then mesh is another concept, mesh both on the front haul as well as at the level of the user device for increasing resiliency and robustness of the system, as well as potentially increasing the capacity. Okay, so we are close to the end of our time here to give some time for questions. So maybe I will stop with this. So this is just to talk about new threats that we expect in the 6G era. First of all, yeah, as usual, we expect a whole new range of endpoints and networks as endpoints. That's what this sub-networks mean, like I just talked about that. So if you really believe that we'll be interconnecting all these small sub-networks, then that could pose new threats. Then some of the other things that are starting to happen in 5G, like the open interfaces and the disaggregation, and then the multi-vendor software, all of these bring new threats to the network. And then the whole idea of deploying the network as software on multiple cloud types of cloud with different types of acceleration. So vulnerabilities are going to explode with all these things. And so we need a whole new range of technology enablers to solve these new security problems, like trusted execution. I mean, these are themes that are starting to be researched in many organizations, and we are trying to build our strengths on that so that we can bring all this into the system in the future. And quantum safe cryptography is going to be quite important, because the system that's deployed around 2030 is going to be there till 2040 before we introduce the next generation after that, if that's going to happen. So there's quite a bit of work to be done on the security space. So let me just say that the research is not done in isolation. Nokia and Nokia Bell Labs works in many different consortiums. You may have heard of HexaX. We lead that in EU. This is a European Union funded research project. We have Finnish government funded research projects. And in the US, NextG Alliance, and then RINGS is about to start. That's one of the programs that we are participating in terms of providing funding. And NextG Alliance is run by ATIS, which is focusing on the next G from a North American perspective. And they're competing, for example, with a lot of organizations in Asia, especially in China. So these are some of the sort of 6G research organizations from an industry, academy, collaboration perspective. So basically, I'll conclude with that. So the main messages are the future is going to be different with the connection of digital, physical, and human worlds. We should expect to unleash the human experience even more than what mobile networks have done so far. And we achieve that with the extreme capacity networks, also providing low latency and synchronization. And of course, a trusted platform with all the security and privacy would be critical for that. So that concludes my presentation. Thank you very much.
Okay, thank you very much, Harish. That was a really interesting talk. We have time for questions, and you can leave your questions in the chat. And I also see Yasman has a question, so please go ahead.
Thanks for the wonderful talk. So my question goes back to the first part of your talk when you talked about DeepTX, DeepRX. Are you envisioning a sort of similar structure across layers, like neural network sort of replacing, let's say, medium access? And given that this will be sort of like a multi-agent problem then, because every device is trying to kind of maximize its own benefit. So yeah, I'm wondering if you can provide some insights on that.
Yeah, actually, that's a very good point. So I didn't have time to talk about it. We are actually working in that space as well. Like, what can be the role of multi-agent reinforcement learning for access problems like interference management and multiple access? How do we coordinate the different devices automatically, right? We could think of extreme versions like, slotted Aloha type access, random access. And then on the other extreme, you signal that you need resources, and then the base station allocates resources. And then you send, the device sends the packet. So we have these extremes. And today we sort of decide arbitrarily somewhat, because we say, okay, we think that the traffic pattern like this needs scheduled access, whereas this traffic pattern could live with random access, etc. We're trying to work on this sort of problems to automatically derive the best protocol. So it's a combination of scheduler design as well as the access mechanism to be learned automatically. Yes, there's a work on that as well. But it's not as mature as the lower DeepTX and DeepRX. Right?
Mm-hmm. Yeah. Great, thanks.
Any other questions? I'll jump in with localization. Arguably, the situation looks optimistic with more and more carrier aggregation happening for mobiles, talking to multiple base stations at once, and the use of a wide range of sub-6. Well, besides millwave, the current use of a wider range of sub-6 frequency bands are all reasons for optimism. Do you think yet we need even more frequency and even more base stations in order to achieve the indoor localization that applications need, or might we be already there?
Well, I think it comes down to the accuracy that you want, right? So we believe that we need sub 25 centimeter accuracy for the factory floor. This is what we are told, right? From Bosch, for example, they are looking for solutions for that. Now, if you want to get to that kind of accuracy, I think, yes, the bandwidth, and that's what the carrier aggregation might help with, right? So multiple bands and bandwidth is only one factor, because non-line of sight localization is very challenging. The trilateralization approach that we all rely on assumes that you have a line of sight link between the device and the cell, right? And so that's where the problem is. Like, so if you have non-line of sight, then the accuracy degrades very fast. And so to achieve the line of sight, we are requiring that we need more than more access points, more dense access points. That is the real reason. For any given location, yeah, 3 is enough. But the problem is we don't know which 3. So we basically have to deploy several, and then maybe 3 out of the several would have line of sight links to the device. So that's what we're observing.
Okay, we're up against time. So is there a quick question out there?
Yeah, just follow up the question. Is any plan in CC to integrate with Wi-Fi 6 or 7?
Yeah, so cellular Wi-Fi integration is more of a coexistence. I think we did work on like so some sort of I forget what it's called, like a joint system. So you could use Wi-Fi downlink for boosting the capacity of cellular, right? Like, so in an indoor deployment, if you have a cellular deployment as well as Wi-Fi, then you can route your packets over both cellular and Wi-Fi on the downlink, and then the uplink is based on cellular. These sorts of ideas were done, but they haven't really taken off. We even went to 3GPP and standardized some of these joint access mechanisms, but I think, yeah, I don't know, license assisted access, etc., hasn't really taken off, in my opinion. It's used in a limited fashion. So yes. What's happening now in 5G is more like 5G itself is trying to create its own version of unlicensed access, but with full coexistence with Wi-Fi.
All right, thanks.
All right, so with that, we are past time. So I just want to, remains for me to thank Harish so much for this really interesting talk, and see you all next time in the seminar series. So goodbye for now, and thank you, Harish.
Thank you very much. Yeah. Thanks.
Thank you, Harish.